Hello everyone. Uh, as you know that I have already defined the dot cancellation law for holonomic constants, and it was del Ri over del Qk is equal to del Ri dot over del Qk dot. Here Ri is the position vector of the ith particle and Qk is the generalized coordinate. Now we will prove by taking an elliptical wire is placed in xz plane. We can write the Cartesian coordinate for the elliptical wire like suppose alpha is the generalized coordinates and a and b are the time dependent constants. So here if I find the value of the x dot here, it will be equal to a dot cos alpha minus a sin alpha alpha dot, and z dot will be equal to b dot sin alpha plus b cos alpha alpha dot. Right, now if I find the value of del x over del alpha, then you know that it will be equal to minus a sin alpha, and del x dot over del alpha dot will be also equal to minus a sin alpha. Similarly, if I find del z over del alpha, then it is equal to b cos alpha, and del z dot over del alpha dot is equal to also b cos alpha. So we can prove here that the two values here, del x over del alpha and del x dot over del alpha dot, are similar, and similarly del z over del alpha and del z dot over del alpha dot are also equal. So by taking this example, we can prove the dot cancellation law. This is a very important example to understand the generalized coordinates. Suppose the two particles are freely moving in three-dimensional space. This is particle number 1 say, and this is particle number 2. So you know that these will have the Cartesian coordinates like suppose x1, y1, z1, and p2 will have the Cartesian coordinates x2, y2, and z2. Now if you have to specify the position of this dynamical system, which is consisting of two free particles and there is no restriction between them, so we will require there will be 6 Cartesian coordinates to specify its position, or we can say that there will be 6 degrees of freedom for this system. Right, now if I put a restriction here, that the distance between, suppose distance between P1 and P2 is fixed. You know that when your P1 P2 is fixed, then we can take it as a constant, and it will produce a constant equation, and that will be of the form, we can write it as x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So here now the independent coordinates will be here, because there is one restriction. So here independent coordinates will be 5, and these are called as the generalized coordinates, right? In earlier case, when the two particles were freely moving and there was no restriction between them, then the degree of freedom was 6, or we require 6 Cartesian coordinates to specify its uh, position. But here we require 5 generalized coordinates to specify the position of this dynamical system, and those generalized coordinates for the any particle can be written as like q1, q2, q3, q4, q5. So for any particle. Now the other thing which is very important here, you have to understand that these 5 generalized coordinates may have or may not have the Cartesian coordinates, in which the earlier case when the two particles were freely moving and those were having the Cartesian coordinates x1, y1, z1, x2, y2 and z2. So these q1, q2, q3, q4, q5 may have or may not have any one of the Cartesian coordinates. Thank you.